Good morning. Okay, so Jane's given a really comprehensive overview of safe use of a broad range of A3 and A2L. So I'm going to give a slightly more concentrated view on flammables in small commercial applications. So we're going to cover a little bit about hydrocarbons and why. We'll talk about the characteristics and the flammability. We'll give a quick reference to the regulatory standards and then get into some of the things that have changed and some of the good practice guidelines that we've discovered as part of our journey through the whole hydrocarbon program. So first point is why hydrocarbons? Now, I think it's clear to say that we've gone through more of an evolution and a revolution. And part of that is to smooth that process change through the industry. Right away from components through to people like us who are manufacturing equipment, to you guys who are actually looking after it in the field, onto recyclers, the use of hydrocarbons is a relatively achievable step change. And complementary to that, it's a really great fit with getting lower greenhouse direct and indirect emissions. And what I mean by that is looking at the energy efficiency, but also the emissions when we choose to release hydrocarbons into the atmosphere. And really, in terms of technology, we've been able, and the component suppliers particularly, have been able to piggyback on technology from domestic refrigeration. So we really tap into the high volume industry and getting access to that sort of technology that allows us to make these efficiency step changes. Now, I make no apology. I will duplicate some of the content that Jane covered. Us humans can probably need 5 to 7 repetitions to actually embed information. So this is 2 goes at it right now. So just looking at following up on the hydrocarbon piece. So as a refrigerant, they are environmentally friendly. They are very efficient. They're relatively easy for us to handle as fluids. They are heavier than air, so they drop, and that needs to be considered, particularly in low applications, basements, etc. But they are non-toxic, and a big but, they are flammable, and we have to deal with that flammability issue. And I think from experience, that whole flammability piece, yes, it's changed the way we design refrigerants, the way we design refrigeration systems, but it has improved the respect that we have for the use of those refrigerants. I think if I look back, we got a bit lazy and a bit complacent with HFCs, and the flammability issue of hydrocarbons has brought that back on center, and we do manage risk much better. And we are much more thoughtful about how we handle refrigerants. If you look at the flammability, the benefit of hydrocarbons is the global warming. But typically, when we lower the global warming, we increase the flammability, and it's some kind of seesaw. And we've never hit that utopian position where we have great global warming potential and low flammability. That doesn't exist. So we're constantly trading off one against the other. And if we just look at those refrigerants just for a moment, and you'll recognize most of the refrigerants down the left, and Jane touched on some of those as well. When we get down to the hydrocarbons, we get by far the best global warming performance in the red box. They are the lowest global warming in the small refrigeration industry sector. Obviously, there's CO2, etc., lower, but practically hydrocarbons achieve the lowest GWP, and they are relatively easy for us to use. Okay, so we get all the benefits, but we do have to deal with the flammability issue. And just reiterating a slightly different way, information that Jane touched on, in terms of creating a flammable environment, and this is something we need to bear in mind when we're actually looking after product in the field, and to a point we have complete control over. We need a source of ignition, we need a concentration that is flammable, and we need refrigerant release to actually create a potentially flammable situation. Now, in use, we are in control of all of these. We're in control of source of ignition. We're using brazing torches. We're in control of where the product is when we're working on it. When we look at the concentration, we're in control because we can put a meter in to actually measure the concentration. And often you're either going to a product that's released refrigerant, so it's not in the first place, or you are releasing refrigerant as part of the remedial work. And you are in control of both of those. Okay, so by and large, we are in control of the potentially flammable situation. Okay, so we can actually manage that situation as part of our role in remedial works on product. And part of that is creating this zone of exclusion around the product. Okay, this should form part of your risk assessment when you actually rock up to actually conduct any remedial works. But I think the key thing here is, yes, we recognise these three elements need to be present, but we are in control of those. Just taking that one step further, I don't intend to go through loads of numbers, but there are a couple of important numbers that we need just to touch on. So focusing more on the hydrocarbons, and I use the likes of 134A and 1234YF as references. The auto-ignition temperature of refrigerants, whether they're flammable, lower flammable, or highly flammable, is all in the same ballpark. Okay, if we're considering the use of brazing torches, the temperature of a brazing flame is way above any of these ignition temperatures. Okay, so it sort of doesn't matter which refrigerant it is. Okay, because whether it's 134A and we're creating very nasty chemicals, when you see that nice green flame, when you actually put R134A in the presence of a brazing torch, which is toxic, or whether it's hydrocarbons that actually ignite, they all have adverse reactions to the presence of flame. Okay, it's fair that hydrocarbons are flammable and explosive, but other chemicals do have adverse properties as well. Okay, so the key is that we remove those from being present when we're actually doing remedial works. And also we have something called the practical limit, which is derived from the lower flammability limit. The practical limit is nominally 20 to 25% of the lower flammability limit. Now, the numbers you see there, if we take R290, is 0.038 kilograms per cubic meter. Okay, the practical limit, and you'll notice I've changed that to grams per cubic meter, and I'll explain why. The practical limit is around 10 grams per cubic meter. If you're in a building, that 10 grams can be extrapolated to the room size that that product can exist in. Okay, and the reason it's in grams is when you look at the data plate on the appliance, the quantity of refrigerant is usually in grams. Okay, so we don't have to do a conversion. And typically, dividing the quantity of refrigerant by the practical limit gives us the volume of room size that will deal with eliminating any concentration of hydrocarbon refrigerant. And an example has been done here. If we've got a 150 gram charge limit, which is the current working limit of a small hydrocarbon system in a building, then if we divide that by the 10 gram practical limit, that gives us a room size of 15 cubic meters. And typically that's a room of 2.4 meters by 2.4 meters. That's a relatively small room to house a hydrocarbon refrigeration unit. Okay, so it gives you a way of actually doing a sanity check on doing remedial work and knowing how much room you need to handle that charge rate. If we then look at the governing standards, okay, Jane talked about EN 378, and that's very applicable for the larger commercial and into industrial, light industrial sector. For small commercial systems, It's governed by EN 60335. There's two key elements. One is part one, which is general safety, and this is general electrical safety. And then we have a very specific standard, is EN 60335-2-89, which is targeted towards the small refrigeration appliances. EN 60335-2-89 is currently being updated, and we should see the update in the next couple of months. And that potentially allows us to use more hydrocarbon refrigerant. The amount of hydrocarbon refrigerant currently in small systems is limited to 150 grams. But that is being increased to somewhere between 300 to 500 grams, but it is conditional. Okay, there are some design changes that we will have to consider in the use of higher charge weights of refrigerant. And that will require a change in labeling, which I'll touch on in a moment. Excuse me. It will require changes in equipment design and changes in equipment testing. And more importantly, it will require some changes in the responsibilities of the end user and installer to ensure that equipment is suitable for use in that environment. Okay, and I'll touch on those in just a moment. So if we just look for a moment at some of the design changes, I've got a very simple diagram here. In terms of design changes to use hydrocarbon, it's essentially trying to reduce the system volume. So, excuse me. So we've aimed to minimize the size of the compressor, because the compressor body normally houses refrigerant. We've reduced the size of the tubing size of the condenser. We've reduced capillary sizing, and we'd also reduce the size of the evaporator tubing. Typically, if we go back 5 to 10 years, condensers would be in 3/8 tubing and evaporators would be in 3/8 to 1/2 inch. Now the size of both those components is typically down to 5mm tubing. This is all designed to reduce the charge volume. And although hydrocarbon typically requires 40% of the volume of HFC system, we've seen much bigger charge reductions. So systems with 300 to 600 grams of 404A could easily be down to 120 grams of hydrocarbon. Okay, but what that means is that there's some consequential requirements around being much more accurate in terms of charge weight, and much more diligent in ensuring systems don't get blocked. In terms of general good practice, this is a fairly busy diagram, and I'm going to pick one or two things out of this. But bearing in mind that we are using hydrocarbon refrigerant, typically we'll start at the top about understanding failure mode. So in understanding the failure mode a refrigeration system, we recommend certain activity. Okay, the first thing is check the labeling. Now, that you should do that on any refrigeration system, but being very clear on the nature of the refrigerant, that it is a hydrocarbon, not a HFC, is important. Okay, and understanding the charge weight is really critical. Charging by gauge is not recommended with hydrocarbon due to the sensitivity of the charge weight. In design and manufacturing, that charge weight is really critically managed, and that needs to be maintained in the field. So charging on scales is much more useful than charging by gauge, particularly as we want to try and keep the gas charge below 150 grams. Now, before you start, we recommend that there's a pat test done before you start to actually make sure you do actually work on a safe system. Historically, the pat test is done at the end, and that's still important, but we do recommend that you pat test to start with to make sure it's safe. James talked about the purging process, and that's absolutely correct. But from experience, we absolutely recommend you don't unbraze systems, but you cut systems. That's ensuring you're not trying to purge something with a blockage. And by cutting, you actually ensure you don't expose hydrocarbon to flame. I'm not going to go through every point on here, but the other key component is always now to replace like for like. More often, ATEX components are being used on the inside of refrigerators. So just dropping in a multi-fit motor that we happen to carry into inside of a cabinet is no longer really possible. They should be changed like for like. Many new ATEX motors are also electronically driven to drive energy savings. So we need to ensure we're replacing with the same component. And the other point is, whilst R290 is the most common refrigerant, R600A is also in use, and R600A will operate on a vacuum. Okay, so ensuring we're charging in through the high side and ensuring that we are removing gauge lines in the off state is really important. And the last point here is around charging. Because the charge weights are very critical, and if I look back to the HFC systems, we could be within 10 to 20 grams, and it would be okay. With small hydrocarbon systems, we are probably in the realms of 2 to 3 grams. So being very accurate around charge weight is really, really important. Just moving on in terms of other sources of leak potential and ensuring that we are diligent around making sure we don't lose refrigerant. Use of Schrader valves, they are becoming more widespread with use with hydrocarbon because it enables easy access into the system without brazing and without line taps. Just making sure we're accessing them and replacing them correctly. We do see situations where the cores are left in during brazing and then they do melt. Use of line tap valves is a very temporary source of accessing a system. Line tap valves shouldn't be left on as a long-term access into a hydrocarbon refrigeration system. Similarly, pressure switches, they should be coded. Capillary tubes, evaporators, condensers, just ensuring there's no rubbing of lines to ensure we don't get leakage caused by abrasion of copper tubes, and so on. So I'm not going to go through this in any detail. A lot of this is things that you already know, but it's just maybe a revision session. And then moving on, I just want to share some of the learnings that we've had with the use of hydrocarbons. So in terms of benefits, hydrocarbons, as we said before, have very similar thermodynamic properties and very similar service requirements, just require stronger management of risk. There's no recovery requirement below 150 grams. And provided the room size is a decent size, they can be vented or more usefully try and vent outside the building. They operate at lower discharge temperatures, which is always good for the system and the long-term reliability. And we do note lower compressor wear, mainly because of the lower discharge temperatures and pressures. And we do see, obviously, lower charge weights giving us potential for less liquid return, which should give us better system reliability and improved efficiency. So we're actually saving energy in terms of the performance of the refrigeration system. But some considerations just to bear in mind. Just be mindful that with the less refrigerant charge, we do need to be mindful of product in very low ambient. So customers putting product out in external buildings, in normal ambient in the winter, we can suffer lower condenser performance. And the same thing goes with hot gas defrost on freezers. We have a preference personally for hot gas defrost on freezers because removing electric defrost heaters is always a good thing in the presence of hydrocarbon, clearly. But if if electric defrost heaters are used, then they have to be chosen with some kind of device on them, whether it's a Clixon or heat limiting device, to be 100 degrees C below the auto ignition temperature, which we touched on earlier. Be mindful that R600A can operate in a vacuum. Just be mindful when you're removing charging lines, and we recommend removing them with the system off when the system is equalized. Don't want to do all the hard work of vacuuming out and charging a system only to pull air in. And lastly, on this slide, charge weights are very low and very sensitive. So looking at getting shorter charging lines off the manifolds, or even consider charging through capillary tube, will help you manage the accuracy of charge weight and manage the losses associated with removal of charging lines. And lastly, in terms of the learnings, and I've just dropped a couple of factory slides in here, but it's equally as relevant in the field. And just to reiterate, from our own perspective, it's always safer to cut joints, disassemble pipework. You can unbraze if you can purge correctly, but we always prefer to cut joints just because we actually reduce the risk of igniting hydrocarbon. And lastly, whether you cut capillary with, and this is just a small tip, whether you cut capillary with capillary cutters or with a hacksaw, because the small charge weights of hydrocarbon make it much more critical, ensuring we don't have badly formed capillary joints is also will have quite an influence on the system performance. So we always recommend cutting capillaries 45 degrees. We've done lots of testing, and we find that we get the best flow performance through the capillary tubes by cutting in that manner. So moving forward, we touched on the redraft of the regulation of EN 60335 Part 2-89 to actually let us use more refrigerants. Now that doesn't come free. What it means is that as manufacturers, we will have to label product with a minimum room size. And under the guidance of the standard, it must be checked by inspection. Now, it's not clear who that inspection responsibility falls to, but it's most likely to be either the installer or the end user. But bearing in mind that this has to be addressed before the product's actually left on site, this will be probably a requirement of the install team to actually ensure that we make sure the product is suitable for the room it's going into. Okay, we touched on the calculation a little earlier, but the product will be, if it's containing more than 150 grams, it will be required to have a room size label on it. So you need to watch out for that and also do some cursory calculations to ensure the room is big enough before leaving the product with the customer. The refrigerant parts should be protected and should not be accessible. The pipework must not be accessible, it should be manhandled. And often on large vertical refrigerators, the pipework at the top is quite a useful aid to grab hold of the product, but that will not be possible with higher charge weights. Now this is with a charge weight greater than 150 grams. From a personal perspective, we will try and avoid going higher than 150 grams for the obvious reasons, but on blast chillers, larger multi-decks, it's more than possible that we will start seeing larger charge weights. The design will have been vibration tested to ensure we don't have advanced fatigue during use, which means that when we change parts and change pipework, they shouldn't be modified during that repair. And lastly, to avoid the potential for concentration, equipment will be tested to ensure that we don't get high concentrations of hydrocarbon should the product leak. So there may be additional airflow and sensory equipment fitted. So clearly that must be observed and maintained during the repair work. So just to wrap up, to ensure all of this is achieved, just touch on risk assessments. I think this is fairly well embedded. Risk assessments have to be specific, not generic, and they focus on a number of criteria. I'm not going to go through them all. The biggest one is the first one, is around people and communication. Just ensuring that when we are doing remedial works, we are clear to the people around us, and we're communicating to them what we're doing, how we're doing the work, and what the risks associated with those are. That then rolls onto the location, ventilation, fire management, and general awareness, and making sure that we have the right technical equipment to ensure we're operating safely. I think it's pretty well embedded. But when we're dealing with flammable product, whether that's an A2L or an A3 refrigerant, an advanced level of care is necessary. Most of this is covered in the City and Guilds training. So this is just a bit of a snapshot. And lastly, which is the taken on subject of risk, is understanding DSEAR. This is Dangerous Substances and Explosives Regulation from 2002. And I'm not going to dwell on this, but this is an area where this is not widely communicated. But this is just ensuring that we are addressing the hazardous nature of the substances that we're using. And this is not just hydrocarbon refrigerants. This is any product that is potentially explosive. And that's right the way down from refrigerants to paint. You can see a list there of those products. So if this is new to anybody on the call, then I suggest you go and research it. So I'm not covering it in detail here, but taking consideration of DSEAR and risk assessments is showing that you are mitigating the potential risks of explosive substances when you're working. So thank you. Thanks for listening. And I think we're due for any questions now, Lisa.